Hello everyone and welcome to this presentation on one of the most significant evolutions in the history of the internet, the IP address crisis. My name is Praj Mahiman and today we will be exploring the transition from the legacy IPv4 system to the modern IPv6 standard. We will analyze the exhaustion of address space, the temporary relief provided by network address translation or NAT, and the architectural improvements found in the 128-bit IPv6 structure. This presentation is part of the computer networks course focusing on the network layer and how it manages global connectivity in an era of exponential device growth. What is an IP address? To understand the crisis, we must first define the fundamental role of an Internet Protocol address. At the network layer, an IP address serves as a unique logical identifier for every interface on a network. Much like a physical mailing address ensures the letter reaches the correct house, an IP address ensures that routers can move data packets across multiple networks to the correct destination. Specifically, we are looking at IPv4, which has been the standard since the early 1980s. IPv4 uses a 32-bit addressing scheme in dotted decimal notation. This is represented as four octets, each ranging from 0 to 255. Mathematically, a 32-bit system allows for 2 power 32 unique combinations, which equates to approximately 4.29 billion addresses. While this seemed like an inexhaustible resource during the Internet's infancy, the rise of personal computing and global networking quickly changed that perspective, especially the growth of production of smartphones, IoTs, like that. IPv4 address exhaustion crisis. The crisis refers to the depletion of the unallocated pool of these 4.3 billion addresses. In the late 1980s and early 90s, it became clear that the exponential growth of internet connected devices would eventually exceed the capacity of IPv4, that is that 4.3 billion users. So several factors accelerated this. The explosion of mobile devices, the always on nature of broadband connections, and more recently the Internet of Things. Official exhaustion occurred in stages. IANA, the Internet Assigned Numbers Authority, allocated its last blocks of address to the five regional Internet registries back in February 2011. Since then, we have been operating in a state where new IPv4 addresses are scarce and often expensive to acquire, forcing the industry to adopt efficiency saving measures. Here comes the classful versus classless addressing. Originally, addresses were allocated using classful addressing. This divided the space into Class A, B, and C. Class A supported 16 million hosts but was only available to 128 organizations in the whole world. Class B supported 65,536 hosts and Class C was limited to 254 hosts per company or organization. The problem was a lack of granularity. If an organization needed 500 addresses, Class C was too small, so they were given a Class B block, wasting over 64,000 addresses. To combat this, CIDR (classless inter-domain routing) was introduced in 1993. CIDR uses variable length subnet masking (VLSM), allowing us to ignore the rigid class boundaries. By using a prefix, for example, like /23, /24, or /20, etc., we can provide exactly 150, exactly 510 host addresses like in /23. This significantly slowed down the exhaustion rate. This significantly slows down the exhaustion rate by ensuring that address blocks were sized appropriately for the actual need of the for the network. So here comes the hero of our story, network address translation. While CIDR improved allocation, network address translation is a technology that truly extended the lifespan of IPv4. NAT allows a single unique public IP address to represent an entire private network. Like inside a local network, we use private IP address ranges such as the 192.168.x series program. These addresses are not routable on the public internet. The NAT enabled router the NAT-enabled router sits at the edge of the network. When an internal device wants to communicate with the outside world, the router translates the internal private source IP into its own single public IP. Like the NAT intercepts the packet that is transmitted from the source IP to the network. This allows hundreds of devices to share one public address, drastically reducing the demand for unique IPv4 addresses globally. So, so theoretically, we know what is NAT, but we don't know how it performs, how it processes, and how NAT maps uh, private IPs to the public IPs. To keep track of these public connections, the router maintains a NAT translation table. It uses port numbers to differentiate between different internal devices, a process technically known as PAT, port address translation. When a packet leaves the network, the router records the internal IP and source port in the translation table, then swaps them for the public IP and a new unique port. When the response returns from the internet, the router checks its translation table, finds the matching port, and forwards the data to the correct internal host. This mechanism also provides a layer of security, as internal IP addresses are never exposed to the public internet. Nobody can see the private IP address. They could only see the public IP address, making it difficult for external actors to initiate unsolicited connections to internal devices. IPv6, the 128-bit revolution. Despite the success of NAT, a permanent solution was required. That solution is IPv6. IPv6 moves from a 32-bit system to a 128-bit addressing scheme. To visualize the scale, IPv6 provides 2 to the power 128 addresses, which is approximately 340 undecillion. This is an astronomical number, ensuring that we will not face another address crisis for the extreme future. IPv6 addresses are written in hexadecimal and separated by colons. A key feature of IPv6 is address compression. To make these long strings manageable, we follow two rules. Leading zeros in any block can be suppressed. A single contiguous string of zero blocks can be replaced with a double colon. This streamlining makes the transition to a much larger address space practical for human administrators. IPv4 versus IPv6 header comparison. Beyond just more addresses, IPv6 introduced significantly architectural improvements. When we compare the headers, we see that IPv6 header is a fixed 40 bytes, whereas the IPv4 header is a variable, varying from 20 to 60. The designers of IPv6 removed several fields to simplify packet processing. For instance, the header checksum was removed because modern link layer protocols already perform error detection. Fragmentation is no longer handled by routers. It is now the responsibility of the source host. Furthermore, IPsec internal Internet Protocol Security, which was an which was an optional add-on for IPv4, is built into the base architecture of IPv6. These changes allow modern routers to process packets at much higher speeds with lower latency. So here is the simplified structure of IPv6 area. The source IP, destination IP, payload length, and flags. So let's the future of global networking. The transition to IPv6 is a long-term global project. We currently live in a dual stack environment where most modern OS and routers run both protocols simultaneously. As we look at the timeline, we see that while the IPv6 standard was published in 1998, it took the actual exhaustion of IPv4 in 2011 to trigger mass adoption. Today, major service providers, mobile networks, and cloud infrastructures have largely migrated to IPv6. The goal is phase, a gradual phase out of IPv4, leading to a more efficient, secure, and infinitely scalable global network. You can see yourself you can see yourself in using a command prompt. You can just use ipconfig and you can verify that you have uh, one IPv4, the IPv4 and the IPv6. Okay. Next thing. In conclusion, the IP address crisis was a pivotal moment in computer science that forced us to rethink how we manage global resources. We have moved from the right classful era to the efficiency of CIDR and NAT, and we are now firmly in the era of IPv6. Understanding these protocols is essential for any networking professional. The shift to IPv6 isn't just about having more addresses, it's about a more streamlined internet where NAT related complications disappear and peer to peer communication becomes more direct and secure. As you continue your studies in computer networks, I encourage you to look at your own network configuration. Use tools like ipconfig or ifconfig to see these protocols in action. You will likely see your link local IPv6 addresses and your NAT provided private IPv4 addresses working side by side. This dual stack reality is the bridge to the future. And honestly, as BTech students, this is a classic example of how technology evolves. We don't just throw things away, we build layers of solutions. Think about it next time. You connect to the VIT Wi-Fi, your request is probably going through NAT, jumping across routers, maybe even tunneling through an IPv6 network. It's a lot of work happening in milliseconds just so you can watch a reel or check your grades. Think about it. Every time you play a game online or stream a movie, these protocols are working in the background. NAT is translating your IPs, CIDR is managing the blocks, and IPv6 is slowly taking over the heavy lifting. It's a perfect example of how engineering adapts to crisis. I hope this presentation has provided a clear and professional overview of the network layer's evolution. Thank you.